My research is about enhancing imaging resolution and depth with adaptive optics, focal modulation, two-photon microscopy. I developed a novel method to significantly suppress background noise, thus improving imaging resolution and depth. First, I will start with a general introduction. Next, I will go over my theory and hypothesis, and then review the related research in the field done previously to my experiment. After that, I will show you my experiment and method in detail, and finally display the results and my conclusions. So in imaging, image quality is limited by aberrations, absorption, and scattering. On the left, we can see how the image is distorted due to aberrations from the rain, and on the right, we can see how this fog causes the absorption and scattering of photons, so the image is lost far away. Biological imaging is subject to the same degradations. So the figure shown illustrates the imaging of a biological sample, and aberrations are introduced by the cover glass and variations in optical index across the biological tissue. Furthermore, structures in the optical path create more background noise. And I developed a method to correct for the aberrations and to suppress background scattering. Improving bioimaging is critical for new scientific discoveries and medical applications. Last year, 3 scientists won the Nobel Prize for their pioneer research in optical microscopy. So an optical wavefront can be described by an electromagnetic wave. And my hypothesis is that when the illumination light of a microscope is modulated with a certain frequency, then the resulting image will also be modulated with that same frequency, but the random scattered light will not be. This way, we can separate the oscillatory component from the non-oscillatory component, which effectively eliminates background noise. The figure at the bottom of the slide illustrates Fourier analysis. So the Fourier transform of a sinusoid can be represented as 2 impulses at plus or minus the frequency of that sinusoid. And since any function can be composed of a summation of sinusoids, by taking a Fourier transform, we can separate signal from noise in the frequency domain. In 2008, researchers at the National University of Singapore developed focal modulation microscopy to suppress background noise. Shown is the schematic of their experimental setup. In their research, they used a piezoelectric actuator that moves up and down to modulate the optical path length in a single photon confocal microscope. In my research, I used a deformable mirror to apply spatial time-dependent phase modulation to a 2-photon microscope. And the phase applied can be represented by the equation shown here. The general phase shape is that of a curved ramp. And the reason I applied this phase is because it provides effective background rejection. The key differences between my research and the previous research is that, 1, I applied my phase modulation to a 2-photon microscope instead of a single photon confocal microscope, and 2, I applied a complex phase that is a function of both time and space instead of moving the mirror up and down. Shown is my experimental setup. My research utilizes the adaptive optics 2-photon microscope developed by Tao and Cubby in 2013 at UC Santa Cruz. In their research, they used a deformable mirror to correct aberrations real time in live tissues. In my research, I used this deformable mirror to apply phase modulation on top of the adaptive optics corrections, which both corrects for aberrations and suppresses background scattering, and that significantly increases imaging depth and resolution. Inside an adaptive optics system, the deformable mirror is the key component, and how it works is illustrated in the figure at the top right. So the deformable mirror consists of a membrane attached to many actuators, and different voltages are attached to the different actuators, or different voltages are applied to the different actuators to cause the membrane to move up and down in various locations to form a variable shape that is desired. Back to my experimental setup, the excitation wavelength is generated by a Ti-sapphire laser, and then the deformable mirror is relayed by 3 sets of telescope subsystems all the way to the exit pupil of the microscope objective, which is the focusing lens in front of the sample. When a phase is applied to the deformable mirror, it is relayed all the way to the microscope objective and thus to the sample. Finally, the fluorescence emission from the sample is collected by a photon collector, in this case, the PMT. To demonstrate my method, I imaged an artificial tissue sample consisting of 1 micrometer green fluorescent microbeads in 5% agarose gel from the depths of 200 to 600 micrometers in 10 micrometer increments. 10 image frames, 512 by 512 pixels each, were taken in a 1-second period with phase modulation. Fourier transforms were also performed at each depth on the 10 intensity values at each pixel location, meaning total 512 times 512 Fourier transforms were taken for image analysis purposes at each depth. Here we can see images collected at 200 micrometers with phase modulation. So 10 images were acquired 0.1 seconds apart, and more aberrations were applied from image A to F as the phase function grew. Finally, the applied aberrations were reduced from image F to image J, completing one full cycle of image acquisition. At image A, no additional phase is applied, so this is the same result acquired by a regular adaptive optics two-photon microscope. And although the collected images seem worse after applying the phase modulation, counterintuitively, I can achieve a much better result after applying my processing method, which I will show later. And here we can see images collected at 500 micrometers. Note how much noisier each image is compared to before at 200 micrometers, even though the same phase modulation was applied. This is because background and random scattering noises are more severe as you image deeper into the tissue, which my method addresses by being especially effective at imaging structures at deeper depths. For image processing, I performed fast Fourier transforms on the images at each depth. So the first AC component, which is circled in red and is associated with the sampling frequency, was saved. This is the desired signal and is what I call the sine signal in my research report. Then the DC component and high-order AC components are eliminated, which removes undesirable out-of-focus fluorescent background and scattering noises. Several processing algorithms were developed in MATLAB, C++, and finally in CUDA, which enabled parallel processing to increase image analysis speed. Here we can see the results using my method and without my method. So on the left is without my method, and on the right is with my method. The out-of-focus fluorescent noise in the highlighted areas was almost completely removed after applying my method, AOFM-TPM, and the random background noise was suppressed, as you can tell by the general background color of each image, where on the left it's a much brighter blue, and on the right it's a much darker blue. The final image was much sharper. The figure at the bottom right illustrates the cross-section along each image along the white lines, and it shows the full width at half maximum. So with my method, the full width at half maximum was reduced to half, meaning that we can better resolve the images using my method. Here we can see even more drastic improvements at 500 micrometers. So the random background noise was very effectively suppressed, and the signal-to-noise ratio was improved by 7 decibels. The full width at half maximum was also reduced to about half, meaning that lateral resolution is effectively doubled. Note that some structures that show up in the left image are not the true structures. These actually constitute near-focus fluorescent background noise, which consists of beads that are near but not at the focal plane. When phase modulation is applied to the image that is at the focal plane will be distorted severely, but the image that is only near the focal plane will not change as much. So we can use Fourier analysis to remove the near-focus fluorescent noise and improve axial resolution. And a clear removal of this noise is shown in the image on the right. To conclude, I successfully developed and demonstrated a novel microscopy method to enhance imaging resolution and depth through a highly scattering medium. I did this through the application of a spatial time-variant phase modulation to an adaptive optics two-photon microscope, and this effectively suppressed background fluorescence and scattering noises. I developed a fast algorithm with CUDA to separate the desired science signal from the background noise, and I reduced image processing time from 15 seconds with MATLAB to just half a second with CUDA. The lateral resolution was doubled, and the signal-to-noise ratio was improved by 7 decibels at the depth of 500 micrometers, and I was able to measure fluorescent microbeads up to a depth of 600 micrometers. For future work, I would like to explore several areas. First, I would like to investigate the phase modulation functions and find the optimal one to provide the best image. Next, I would like to explore the depth limitation of this method for various biological tissues to aid practical use and further improve the speed of data acquisition and analysis to possibly enable video. Finally, the development of a 3D reconstruction tool would greatly aid understanding of the sample that is imaged with my microscope. Here's a list of my references. I'd like to thank the NSF Center for Adaptive Optics and the WM Keck Center for Adaptive Optical Microscopy. I'm especially grateful to Professor Joel Cubby and Dr. Xiaodong Tao for their technical guidance and support, and also to my high school teachers, counselors, and principals for their encouragement. Finally, I would like to thank the Siemens Foundation, Discovery Education, George Washington University, and the judges for your time in making this all possible. Thank you for your attention.